Now, before we go any further and start talking about the mathematical aspects of quantum error correction and fault-tolerant computation, I think it's a good moment to step back and ask a more general mathematical question. Namely, when a quantum channel can be inverted, can be reversed, when the action of completely positive trace-preserving map can be undone. This obviously is motivated by observation that you may have that we took an unknown state of a qubit, we encoded it into a state of 3 qubits, and then the 3 qubits were exposed to interaction with the environment, which induced completely positive map on the system of the 3 qubits. And then we managed to recover the original state. So we managed to undo the action of the environment by inducing another completely positive map, which was due to the interaction of the system of the 3 qubits with ancillas. So obviously it is possible to do it, but the question is, what are the general mathematical conditions for this kind of thing to happen? So I will just take first more abstract approach, and then, but we will talk about the physical intuition behind it. So imagine then you have 2 completely positive trace preserving maps. So those are 2 quantum channels. When I say quantum channel, I mean completely positive trace preserving map. So there's one quantum channel E, another quantum channel R. So let E maps a set of bounded linear operators on Hilbert space H into a set of bounded linear operators on Hilbert space H prime. Bounded is a little bit an overkill here because we are talking about finite dimensional Hilbert spaces, so all linear operators are bounded, but well, the notation is so common, so let me just use this notation anyway. So we have one quantum channel that is then reversed by channel R that takes us from B of H prime to B of H. So the composition of the 2, E followed by R, is equal to the identity. So when this can happen? So now I'm going to show you that the following 2 statements are equivalent. So statement number 1 is as follows. So if given E, there exists a quantum channel R such that R is the inversion of E. So the composition of apply E, then apply R is equal to the identity. That's statement number 1. Statement number 2 is that for any Krauss representation of E, the product of the Krauss operators EI dagger EJ is equal to some number times the identity. Now, the sum number depends on I and j, and if you look at it as a matrix, this matrix is a density matrix. So now, mathematically speaking, it just means that it's a positive semi-definite matrix with trace equal to 1. But as a physicist, you may also ask, is it a generic density matrix, or is it a density matrix of some system? So it is indeed the density matrix of the system, actually of the environment, which is involved in inducing the map E. So let me just first go from 1 to 2. So I'll show that 1 implies 2, and then I'll show that 2 implies 1, and that we'll just get the equivalence. So I'm going to include the environment and the ancilla in our discussion because it gives you a better physical insight into the process. We start with a system, a vector in the Hilbert space H. Apply our quantum channel. So the system gets entangled now with the environment. So you have a system, and this is the environment. The system gets entangled with the environment, and we have a superposition of states of the systems. Now they are vectors in H prime, so each Krauss operator here will take Job psi into a vector in H prime, and the respective state of the environment EJ. So that's your first quantum channel. here comes the second quantum channel. So that entangles the system with the ancilla. So you can see that you have the Krauss operator associated with this map R, Rk, and then the corresponding state of the ancilla Ak. Now we know that the composition of the two gives us the original state, psi, tensor something else. So at this point we know that somehow the entanglement between the system and the ancilla and the system and the environment is magically transferred to the entanglement between the ancilla and the environment. So this is only possible if you if the action of this product of the Krauss operators associated with E and associated with R is proportional to the identity. So each term here should be proportional to the identity, because then you have a term that is proportional to psi. This is the only way you can somehow recover psi. So let's write this condition as the condition that the product Rk with Ej is equal to some number alpha jk times the identity. And if you write it this way, then you can see that this something, the state of the environment and the ancilla, can be now written explicitly as the sum over jk, alpha jk, the state of the environment, Ej, the state of the ancilla ak. So you can see that indeed this is an entangled state of the environment and the ancilla, and our state psi, the state of the system, is recovered. So that's good, but let's see, in order to show this, let's see what this condition tells us about this product, E dagger I Ej. So now I'm going to sandwich between EI dagger and Ej the identity. And then I use the fact that R is a completely positive trace preserving operation, and if it is trace preserving, then the sum of Rk dagger and Rk over all k is equal to the identity. So I just decompose this identity in terms of the Krauss operator, product of Krauss operators associated with R. So and then I look at this pair here and this one here, and I can see that this condition, right, implies that this is proportional to alpha jk and this is proportional to alpha ik complex conjugate. So hence the product can be then written as the product of two matrices, if you wish, alpha ik complex conjugate alpha jk, and you sum over k, and that is proportional to the identity on H. So this product then we write as sigma ij. Now what exactly is sigma ij? You can do the calculations and you can, mathematically speaking, see that this is a Hermitian positive semi-definite matrix with trace equal to 1, but you can also see it in a different way. So first of all, you know that this state here is the state of ancilla and the environment. So it's characterized by the coefficients alpha jk. And then, so this is the pure state, but you can trace over ancilla and get the density operator pertaining to the environment. And if you do this, you do calculations of this time, so you can see easily that the reduced density operator pertaining to the environment has matrix element in the basis EI is matrix element sigma ij. So that's can be written as sigma ij ej ei. So this is just a really density matrix. So we managed to prove at this point that 1 implies 2. So let's go the other way around. So the 2 implies 1. So we assume that we do have this condition, so that ei dagger ej is equal to sigma ij, elements of a density matrix, times the identity. Now what we are going to do, we're going to go to the basis, which is in which this density matrix is diagonal. So that means that we are going to change the set of our Krauss operators. That as you remember, there's always ambiguity about Krauss operators. Given a quantum channel, we can choose many unitarily equivalent sets of Krauss operators. So we are going to use this freedom of choice now and go to the set of Krauss operators in which this density matrix is diagonal. So that corresponds to choosing the basis in the environment and in the ancilla in such a way that this pure entangled state of the ancilla and the environment is in the is written in the Schmidt decomposition basis. So you just pick up the Schmidt basis of the environment and the ancilla, but in this case we are interested in the environment, and then you just only have one index. So this means that you, of course, you have to adjust your operators E and R. So if you do this, you have a set of new Krauss operators acting on the system that corresponds with different states of different bases in the environment. But the nice property is now that this is diagonal, right? So this can be written as a Kroneker's delta ij times some positive number pi that we treat as a probability, and that we know that those pi's add up nicely to 1. So we have this condition, which is easier to understand and interpret. So in particular, you can see that for I and j being different, you just have 0 here. But if they are identical, f dagger I, fi, is proportional to the identity. So that implies right away that fi is proportional to isometry. Remember, for isometry, we have a condition that v dagger v is equal to the identity. So clearly fi has to be proportional to some isometry vi, with the proportionality being square root of pi. So that gives us isometry. So then how can you think about the action of E in this particular case? So perhaps, a good way to think about how Krauss operators, the special set of mutually orthogonal Krauss operator, acts on vectors in H. So in fact, each isometry, say v1 or v2 or v3, will take the space H and embed it in this higher dimensional space H prime with certain probability. So we say that the isometry v sub k is chosen with probability pk, and that's the action of those Krauss operators. This is actually one way of understanding the action of E if this condition is satisfied. So there is a set of Krauss operators that are proportional to isometries, and we choose isometry v1, v2, v3 with probabilities p1, p2, p3, and so on and so forth. And each isometry will be then taking the whole Hilbert space H and embedding this space in space H prime and different subspaces. So the images of H being H1 under V1, H2 under V2, H3 under V3 are mutually orthogonal subspaces. So because of this condition here, right? So if I and j are different, then the product of those two is equal to 0. So that means that it's very easy, in fact, to construct the reverse operation. So your Ri now is equal to Vi dagger. So if you want to apply the reverse operation, you just simply choose the reverse of those isometries. So you for V1, you can reverse the action of V1 with the V dagger one, right? But that reverse will only act on vectors in H1. So the V1 ignores everything which is not in H1, that everything just becomes the kernel, just goes to 0. And it's only H1 that is reversed. So the same for V2. V2 will just ignore everything else, but will just take H2 and maps it back to H. So you can see that because of this condition here, when we apply another completely positive map with Krauss operator Ri given by Vi dagger, we reverse the action of E. That is certainly possible. So this actually proves that 2 implies 1. It's perhaps worth looking at the rather special case, namely when the dimension of H is equal to the dimension of H prime. So in this particular case, the isometry becomes a unitary operator, and you can show that this kind of condition for unitaries means that there is essentially just one unitary operator in this decomposition in the Krauss representation of E. So E is a unitary map, and that's the only possibility when the dimensions are identical. When they are not, when H prime is larger than H, then we can certainly have a room for accommodating this condition, so that we can see that, think about it this way. So Vj takes, for example, j equal to 1, just maps you into one Hilbert space, and it's only V1 that can take you back into H, because then if you look at if your index I is different from j, so let's say I is equal to 2, so if you go from H to H prime via V1, so you end up in H1, and then you want to go from H prime to H via V2, so you know that V2 will just ignore everything except H2. So if you are here, you'll be ignored by V2, and the whole map will just give you 0. So those kind of conditions work nicely when you have higher dimensions on the H prime side. But if the size of H is equal to the size of H prime, then the product of two unitaries can not be equal quite to 0. So if one of them is a unitary proper, the other operator has to be equal to 0. So that means that if we have one unitary in our set of Krauss operators, all other operators of this type have to be equal to 0, or if you switch into a unitary equivalent set of Krauss operators, then all Krauss operators have to be proportional to the same unitary operator. So that's for the case where H is equal to H prime. So this equivalence just gives us some insight when one quantum channel can be reversed by the action of another quantum channel. When we are going to apply it now to a specific case of quantum error correction, where our space H will be the code space, and that space will be embedded in a higher dimensional space, and those maps that we saw here, those isometries, will represent quantum errors.